The Armed Tooth Fairy, or How to Speed Up Things. Investigating vectors. This is an arrow. You can use it to shoot apples off kids' heads, or to shoot teeth out of kids' mouths. Some people use an arrow to show a direction, or to point it at some target. But an arrow can do even more for you. It can act as a vector. A vector? What is that, you might ask? And the answer might surprise you. A vector is an arrow. It has a certain length and it points into a certain direction. And they become very useful when you add them together. I will show it to you. One thing we can use it for is to represent a velocity. If something is moving, it has a certain speed and a certain direction. The length of our arrow then shows the speed and it points into the direction our object is moving.
Oh my God.
Another thing we can represent with vectors are forces. Again, the length of the arrow shows the magnitude and the arrows point in the directions the forces work. Here we can see that force 1 pulling towards the right is stronger than force 2. The right guy wins. A third example for a vectorial quantity is the momentum. The momentum of an object is its mass times its velocity. On a pool table we can see the conservation of momentum in action. Let's have a look at a train passing by at a uniform speed. Now let's imagine a person standing still on the train. Again we mark the velocity vectors. One for the train and one for the person. When we compare them, we find that they are equal. We all can imagine what happens when the velocity vectors of the vehicle and the passenger are not equal. And what if the person is moving on the train? And now let's move the train as well. The man walking on a moving train has a higher velocity than the train alone. The difference between these two vectors is the velocity of the man against the train floor. So this is the first rule of vector addition. Put the tail of the second vector to the tip of the first vector. When they show in the same direction, their lengths just add up. But what happens if one speed vector shows into the opposite direction? The length gets subtracted. Here is the proof. This car drives at 60 miles per hour and the air cannon shoots a ball into the opposite direction also at 60 miles per hour. The speed vectors add up to 0. But there is not only forwards or backwards, but also up and down. So let's see what happens when we add the two motions into different directions. The up and down of the ball and the forward motion of the train. And let's push around some arrows. The blue arrow shows the resulting vector. Now let's put the two movements together and mark the positions of the ball. As we can see, the resulting path is the sum of the two different speed vectors. The ball does not only go up and down, but also keeps its sideways movement due to the train. Here is a little experiment that shows that the ball keeps its sideways movement.
I'm ready. Physics works.
And with that knowledge, we can answer the next question from Eric D. from T.
22. If Earth were truly constantly spinning eastward at over 1,000 miles per hour, during the Red Bull stratosphere dive, Felix Baumgartner, spending 3 hours ascending over New Mexico, should have landed 2,500 miles west into the Pacific Ocean, but instead landed a few dozen miles east of the takeoff point.
Sorry Eric, but you missed a vector. When the Earth is constantly spinning east, Felix Baumgartner, when standing with his balloon on the ground, is also spinning east, and he doesn't lose this sideways velocity. As in the train and ball example, we also have a composite of two motions here. One vector goes up and down, and one follows the spin of the surface, because Felix cannot lose this momentum. A similar case is a helicopter hovering over the spinning Earth. When it is standing on the ground, before its flight, it already has the same sidewards spin like the surface of the Earth. And when it lifts off, it adds a second upwards vector to its movement. Because it follows the spin of the Earth, it can touch down safely without any problem. Here you can see the flight curve with the two velocities added together. But don't worry, Eric D. from T, you are not alone. Even engineers can stumble and fall over forgotten speed vectors.
I'm a structural engineer and I've taken a lot of physics courses in my life. One of the biggest things that caught my attention was planes flying on a spinning Earth, trying to land on north and south runways. Because the Earth rotates from west to east, and things don't seem to line up.
Actually, they do line up. You just have to remember that an airplane that stands still on the runway already has a velocity, the same as the spinning Earth, and it does not lose it. So, in whatever direction the airplane flies, you have to add that speed of Earth's surface to its flight. In my video, An Apple, Earth and a Wet Ball, I showed that for a stable orbit you need a certain orbital velocity, so that the centrifugal force counters gravity. Now that we know how to add speed vectors, we can make use of the spin of our Earth to achieve orbital velocities. Because the rocket's velocity and the spinning velocity of our planet can be combined. Earth spins towards east, so it makes sense to launch rockets in an eastern direction. The spin is fastest at the equator, so it makes sense to launch rockets near the equator. That's the reason why each spacefaring nation tries to have its launch sites as close to the equator as possible. Forces are everywhere. They constantly influence our lives. There are all sorts of them, and they push and pull us around. Newton's first law says force equals mass times acceleration. A force can accelerate a mass. The force and the acceleration act into the same direction. But usually in real life we have more than one force acting on objects. And it is not always so easy to see what will happen to the object. But when we add the force vectors, we can find out the resulting force and acceleration. Physicists often draw free body force diagrams to find out all the forces that act on a body. If you forget to put in a force vector, you will get the wrong result. Flat Earth protagonists always wonder why we cannot easily measure gravity between two masses in a lab, if gravity exists. But they forget one force vector that makes these experiments very difficult: the gravitational field of the Earth, that is much stronger than the effect we want to measure. Sometimes all forces add up to zero. That means the net force is zero, and thus the acceleration is also zero. That's what we call equilibrium. Here is an example. When you stand still on the ground, your weight and the so-called normal force of the ground pushing against you cancel each other out. You feel no acceleration. Here is another little experiment that shows that sometimes an equilibrium can arise all of a sudden and very violently. In the last few minutes of this video, I want to answer another question from Eric D. of T. How is it that gravity can cause planets to revolve elliptical orbits around a single center of attraction? Ellipses by nature require two foci, and the force of gravitation would have to regularly increase and decrease to keep planets in constant orbit and prevent pulling them into direct collision courses. Okay, let's have a look at a simple system. One star and one planet orbiting around in an elliptical orbit. Sometimes it comes closer to the star, sometimes it is further away. When we look at the universal law of gravity, we find that when the masses stay the same, only the distance has an effect on gravity. If the distance is big, then gravity is small, and if the planet comes closer to the Sun, gravity will become stronger. What happens when gravity becomes stronger? It pulls stronger at the planet, so the planet gets accelerated. You can see it here. When the planet comes closer to the Sun, it gets more and more accelerated and orbits faster. But when it orbits faster, the centrifugal force gets stronger, making the planet fly away from the star. And when it flies away, gravity pulls on it and decelerates the planet. At one point, its velocity is so small that it cannot get further away from the star and changes direction again and comes back. It's like a dance. Gravity is dancing with centrifugal force. At each point in the orbit, they balance the planet out. There is nothing magic about it. It's plain physics. Nature does not need two foci for an elliptical orbit. It just needs gravity and inertia. And when you care to look at the formulae for gravity and centrifugal force, you can easily calculate every single moment of an elliptical orbit.